Hello everyone, thank you for coming to my presentation. Today I want to talk about the argument in favor of Rust and the argument based on that it has a lower carbon footprint than other programming languages. My name is Michael Mullen and let's get into it. So the agenda for today is I want to talk about the purpose of why I'm doing this video. I want to give myself some self-promotion going on here because of the work I did for this video. I'm going to go through the problem statement, the hypothesis, and the experimentation parameters of an experiment that I ran to be able to kind of prove or disprove whether Rust is a better environmentally friendly programming language. After which I want to go through what algorithms were used for this test. I will talk a bit about some of the problems with me running this test. And then we'll go over the code and look at the results of the test. So, a little bit of clickbait here. Can Rust save our planet? I'm not sure if you're aware, but a few years ago, there was a lot of articles that came out about Rust's efficiency and what that efficiency means in terms of carbon footprints and in terms of being more environmentally friendly than other programming languages. But a lot of these articles that I read, the only argument that I saw was that they are more efficient. But there was no data given, there was no kind of hard evidence given that Rust was even more efficient in the articles. It was just an assumption made. And this assumption is not a good argument in my mind. So what I want is some real meaty data to sink my teeth into. But of course, no one's giving me that data. So instead of whining about it, I thought, okay, let's just get the data myself. So I got the data myself, and now I'm going to share my information with you. So a little bit of self-promotion. Why have we not seen the data collected by other people? Because it's an extreme amount of work. So my self-promotion here is that I don't normally ask people to like and share my videos, but for this specific video, I put a lot of work into it. So if you did like it, if you think the message is important, I wouldn't mind if you could like it and share it with other people who you think the message might resonate with. This is the first video that I've ever made where I actually spent money to buy hardware in order to give the presentation. I bought myself a little kilowatt doohickey that can measure wattages used and kilowatt hours used. This cost me $70 Canadian, and that money's just kind of gone because I don't get paid for these videos. So if you could maybe pay me in likes and shares, that'd be awesome. Now, more than just like to make me feel good about the work I did for this video is that this topic is important. And if you can like and share this video enough, maybe a real scientist with some, grant money can do a real experiment rather than kind of the weekend scientist napkin math experiment that I'm able to do for this. And maybe we can actually get this idea looked at in more detail with a real rigorous test. So just a warning before we go on. This video is probably going to be a long one. Before I go into all of the data, before I go into the code, I need to explain to you how I ran this scientific experiment, because just the data and the code alone, it needs some nuance and concepts behind it before I can just show it to you. However, the TLDR is yes, Rust is more efficient, and therefore, because it's more efficient, it uses the CPU less. Because it uses the CPU less, it uses less electricity, and therefore less carbon emissions. If you just want to get into all of the good stuff, I'll put a link down below in a comment or in the description where you can jump to dive into the good stuff, so you don't have to hear me ramble about kind of the parameters of this test. So what is the problem statement? The problem statement is that electricity requires the expenditure of greenhouse gases to make. Now, the province that I live in, which is Ontario, has moved to mostly carbon-friendly sources. 92% of the electricity generated in Ontario is from carbon-neutral sources, such as nuclear energy. We get 59% of our energy from nuclear. 24% is from water, hydro, Niagara Falls. 8% of our electricity is from wind, and 1% of our electricity is from solar. However, a lot of places aren't like Ontario. A lot of places are still burning coal. They use a lot more natural gas than we do. The U.S. government, the U.S. Environment Protection Agency, has got a good calculator on the internet that kind of makes a generic case for the usage of electricity in the United States. And this is kind of all encompassing, so it's not like a particular state or a particular city, which is important because other states are like mine, where they use more carbon-friendly sources of energy, and other states use a lot of coal and a lot of other less friendly and less environment-friendly places. But for the entirety of the country, this is kind of the some calculations that they give. One of the important ideas that they present is that 1 kilowatt hour of electricity is basically equal to 0.709 kilograms of CO2 emitted, or it's equal to 0.784 pounds of coal burned. So kind of that's the impact that we want to look at. If we can save, a kilogram of CO2, that's good for the environment. Every little bit helps. So what is the hypothesis, and how are we going to conduct this experiment? The hypothesis is that Rust's efficiency reduces demand on the CPU computation, thus reducing the electrical needs for those computations. The test is that using 6 different web applications, 3 written in Rust Axiom, 3 written in Node.js Express.js, when these algorithms are pitted against each other, when these web applications are pitted against each other, running the same high-level algorithm, the Rust application should utilize less energy than the Node application if my hypothesis is correct. So what are the parameters of this test? I am running 2 different machines. The first machine, which is the machine that you can see me on right now, is my AMD 5950X, and this is my client machine, which is going to be running an OHA benchmarking test upon my host machine. My host machine is a Skylake NUC. It is the Skull Canyon version of the Skylake NUC. So it is a 45 watt TDP i7 6770 HQ processor. It has 4 cores and 8 threads. It idles at 12 watts, so it's just sitting there running Alma Linux 9. It just sits there at about 12 watts, 12.2, 12.4. It's around there. It uses 19 DC input voltage. It has 32 gigabytes of DDR4 RAM running at 2133 megahertz using 2 DIMMs. And the connection to the client machine is over a 1 gigabyte network. And the measurement using iPerf3 is 990 megabytes per second throughput between these 2 computers. So the network shouldn't be much of an issue in this test. Node.js doesn't seem to use multi-threading very well. When I run Node.js, I see it has multiple threads running, but it runs as if it's single-threaded. And so for that reason, I put an Nginx load balancer in front of the Node.js, and I'm running 8 Node.js instances behind this Nginx load balancer to kind of get it so that it's utilizing the cores as much as it can to be more efficient with running these tests. Rust doesn't need this help. It is running perfectly fine using 8 threads with the Axiom framework. All of my tests are using OHA benchmarking, web benchmarking framework. And in these tests, I am always running with 12 concurrent connections. The reason I picked 12 is that it is 1.5 times 8. And 8 is the number of threads running on the client machine. Each test has its own number of throttling, how I rate throttle it. So I'm rate throttling so that we can get a good look at how much electricity is used at different load levels, and that's going to be different for each test. So all of the tests that I use 3 different tests. 2 of the tests, one for Rust, one for Node, is called the file list test. This is a very heavy test, and it represents usage of the Linux file system. It's not reading or writing files, but it is walking over the directory structure from the Linux kernel 6.0 RC3 tree. So it's going to walk over all of the files and directories in the Linux kernel, and it will make a list of all the files and then present it over the web as an HTML response to a request given to the various web servers. So yeah, none of the files were opened, but they were all statted to be able to tell if it's a directory and we need to kind of continue on, or if it's a file and therefore it should be output to on the HTML display. Neither Rust nor the Node.js JavaScript framework used async for this. I originally coded this to use async IO for the traversal of the file system, but both Rust and Node were exceptionally poor under those conditions. I can't fully tell you why that is. I think it's because the web framework is already async, so there was maybe some kind of getting in the way of the framework versus reading the files versus the framework getting in the way there. So I made these both synchronous calls, and they are both recursive. So that does matter for this. After all of the files have been read into a list, that list is sorted, and then it is displayed out to the client. The response given has 77,960 lines, and it is 5,055 bytes of data total in the responses. The rate limits I used were 1 request per second, 2 requests per second, 4 requests per second, 8 requests per second, and for Rust only, I also used 16 requests per second. So the next test is a file test, and this is a very light test, and it represents returning an in-memory web page. So it returns the results of the man2 open web page from man7.org. And I will show you the outputs as we get into the code and see the stuff. But it represents just returning a web page that is cached in memory rather than read from the file system. So it's in the memory of the application as it's running. Therefore, no file system lookups, no reads need to be done. It just spits out the HTML because the HTML is pre-cached in memory. In the case of Rust, the actual man page is baked in to the compilation phase, while in Node, because running is compilation, it is one of the first things which is done upon running of the Node application. The rate limits for this test were 100, 200, 400, 800, 1200, and 1500. And the last test is the user database test. And this represents retrieving data from a Postgres database and responding with JSON output. So this is a much more common use case that you'll see on the web. This is kind of a common REST kind of, it represents kind of a common REST API idea. Both Rust and Node use the very same Postgres database. In that database, there are 1,000 entries representing user data. That user data consists of three fields, a UID, which is an integer, and it ranges from 1 to 1001. The next field is first underscore name. It is a varchar of 80, and all of the values are set to first underscore name. And the third field is last name, which is a varchar of 80, and it is all of the values are set to last underscore name. The total output of running this test is 61,957 bytes. So what are some of the problems with me specifically running this experiment? I lack the physical resources to do a really deep and thorough experiment. Not only am I just one guy doing this on my weekends, but I don't have server grade hardware. I don't have a Raspberry Pi. I really wish I had a Raspberry Pi to be able to kind of look at the electricity usage that a Raspberry Pi can do, and how if a Raspberry Pi could hit the same kind of performance levels as this x86 Skull Canyon NUC I've got, or how close it can get based on performance per watt, that would be. Also, my measuring tool is a kilowatt hour consumer product. It is the P3 International P4460 thing. You can buy it on Amazon. But it lacks kind of precision for what I want. While I can measure kilowatt hours used, the precision it gets down to is per tens of watt hours. And when some of my tests are, 20 watts used versus 25 watts used, that sort of precision loses, the 5 watts of data. 5 watts of electricity usage, because they would both come out as, on the kilowatt doohickey thing, they would both come out as 0.02. So I wouldn't see a difference there. Now, I can make up for this if I ran the tests for a very long period of time, but sufficient amounts of time would be about 5 hours per tests. And that would mean that I'm running this test for 85 hours total. I neither have time for that, and I'm also worried about running my NUC at full capacity for 85 hours, and I'm worried that I might actually just break my computer here. So I don't want to do that, and that's one of the problems with me specifically doing this test, is that I just don't have the resource to do a really, really deep, good job with it. The other problems that are inherent to me running this test is that, like I said, I'm but one man, so I can only code up so many test applications for this. And there are some things that we need to think about, like how would TLS impact these tests? Because TLS is doing hashing, it's doing more communication between the server and the client. How would TLS impact the electricity usage? How would using compression impact these tests? While I can test compression, I don't know what that would mean to... So the machine doing the compression will use more electricity to do compression, but the entire system would use less electricity because less bytes are going through wires. And let's pretend like we're on an internet where there's 7 or 8 hops between us. Each one of those hops would have to do less traffic management. They would have to do less work to handle all that compressed data. But I'm not able to measure that. I simply can't. So yeah, that's another problem with the test. I just don't have the time to do a really detailed test to flesh it all out. I'm hoping to give you a flavor. I'm hoping to give you enough information to whet your appetite so that maybe you look into this, or maybe a scientist with grant money looks into this. I also have a distinct lack of Node.js experience. I haven't touched JavaScript since my college days in 2005. So I haven't used JavaScript in 17 years. This is the first time I've ever used Node.js because Node.js didn't exist when I was in college before. And on a side note here, I'm really impressed about how far JavaScript has come in these 17 years. When I was in college, one of the reasons why I became a systems developer, and I first worked in C, is that I found C so much easier to deal with, even with all the memory allocations, even with all the pointers to pointers, references to pointers, all of that stuff. That's easy compared to debugging in a browser back in 2005. So JavaScript has come a long way, and I can sort of understand why a lot of developers really love JavaScript, because it's not the evil boogeyman that it used to be back in when I was in college. So yeah, if I've made mistakes with the Node.js code, please educate me in the comments. Or even better is if you could make a video with your knowledge yourself. You might enjoy making videos, and I want to see more content, more technical content like I deliver. I'm the reason why I make these videos is two parts. The first part is that I use these videos as kind of a memory dump, so I just kind of put all my knowledge into the video, ship it off to YouTube, and I can forget it. And when I need to remember that, instead of making my brain work to remember things, I go back and watch my own videos and go, oh, that's how I did it. Okay, now I remember how to do things. The other reason why I make videos is that I kind of want to be the change I want to see in the world. And I think a lot of the stuff on YouTube is bad. Um, I don't like a lot of the stuff I see on YouTube. I want to see more stuff like I make, and that's why I'm making them, because I think there should be more stuff like mine. So if you have an inkling to make videos, do it, because I want to watch them. So yeah, let's get into the code and let's see the results. All right, so what we've got on our left is the Rust code. It's a Rust Axiom web framework. And what I have on the right is an Express.js, Node.js web framework application. All three of the applications, so the file list, the file, and the user DB, are all contained within the same source code here. So I don't have to kind of keep recompiling over and over and over again. Before we go on, before I dive into the code, I'd like to make it clear that all measurement of electricity is done upon the NUC Skull Canyon that I have, and the client machine is not being measured whatsoever. Its electricity is not being measured whatsoever. The NUC has nothing but the Ethernet jack plugged in, so there is no monitor connection, there are no USB connections, there's no keyboards, no mice. It is only the Ethernet is connected to it, so there isn't anything else taking up electricity while these tests are being run. The NUC idles at around 12 watts. So yeah, what I want to look at first is the file list test. So this is just your boiler on the left is just your boilerplate to set up the Axiom web server, and I want to look at the get root for /file list. This is going to call the file list function, and this file list function is just making a string of and in this string is just an unordered list and list items in it. To get the list items, I'm going to walk over the file system starting at /mytemp/mainline. So that is the Linux 6.0 RC tree. It is in a make Mr. Proper setup, so there's no objects or anything like that. There's no configuration. And mytemp is mounted as a tempfs. So it is an in-memory file system. The walking requires, it is a recursive algorithm. So the path buff that we pass in, we do a reader on it, and this is from the standard Rust library. And then for each entry that we get out of that, which is either a file or a directory or a soft link, we're going to, if it is a directory, we're going to recursively call walk again. If it is not a directory and it is a file, we're going to turn that path entry that we got from dir into a string. And then we're going to add that string to the file list, which is just a vector of strings. And then we keep going, keep recursing in, and then eventually we have a big long list of all of the files in the Linux kernel tree. The node code works very similarly. So the express.js get is looking for file list, and it is just setting up a string of an unordered list where I walk over, I do a for each of the values returned from this file list function. This file list function is setting up a deck, and this deck is holding the data. So the deck is the version of vector in Rust. Well, no, but it's sort of the same sort of concept. It's a collection that can be used. And the walking means that we will look at the directory presented to the function. And then for each of the items in that directory, we're going to look at if this is a directory item, in which case we're going to recurse into walk again, or if this is a file, we're going to push it onto the deck. And after all is said and done, we will have all of the files in the deck. We will then sort it, and same with Rust, we sort it after we get the list out. And then we will turn it into list items, Rust here and node here, and then we will output it to the client making the request. So what does that look like when I run it on a browser? It looks like this. So it is just a big long list of all of the files sorted alphabetically in the Linux kernel tree. Just a big long list containing the full path. So yeah, that's all it's outputting. And the results for running this in OHA are the following. So here, this is the actual data captured, and then this is all of the rest is kind of my napkin math, and I'll go over it. So when I ran this with 1 request per second, the amount of electricity used by Rust was 16 watts, and the amount of electricity used for Node was 23 watts. For 2 requests per second, we were looking at 19.5 watts for Rust, while Node had 33 watts used. When 4 requests per second were run, Rust was running at 27 watts used, and Node was at 45 watts used. At 8, Rust had 38 watts used, while Node, which was getting close to its maximum, was using 69 watts of electricity. And then the maximum for Node was 9.5. So the last entry here, which is 16, at 16 requests per second, Rust was using 54 watts of electricity. So what that means for a watt to request ratio is that obviously at the amount of watts used divided by 1 is just 16 watts per 1 request. Or with Node, that's 23 watts per 1 request. But as we ramped up the requests per second, you can see that the amount of watts per request keeps going down and down and down until eventually Rust hits 3.38 watts of electricity used per request. And of course, the 0 here represents that node simply couldn't run at 16 requests per second. What that means is if I turn this into a yearly, if I just ran this continuously all year long, the amount of electricity used at one request for Rust would be 140 kilowatt hours used. All the way up to, at 16, I would be using 473 kilowatt hours used. For context, the cost per kilowatt in Ontario is somewhere around 10, 11. There's time of day shenanigans that our electricity companies put onto us. But basically what this means is that even at the maximum workload for this, I would be spending about $4.73 per year to run this test. In contrast, the node test ran from 201 kilowatts if I ran this for a full year, all the way up to 604 kilowatt hours used, running at 8 requests per second for the entire year. What does that mean for carbon output? Like the US government EPA says, 1 kilowatt hour represents what was the value that I looked up? 0.709 kilograms of CO2 emitted. So that means for an entire year, running these tests at 1 request per second, my Rust would use 60.64 kilograms of CO2. I would cause, if I ran this in the United States, in a general spot in the United States, I would cause the emissions of 60.64 kilograms of CO2 emitted for the lightest test with Rust. And at the heaviest test with Rust, I would be emitting 204 kilograms of carbon. And in the case of Node.js, we go from 87 kilograms all the way up to 261 kilograms of CO2 emitted. To put things in terms of percentage, this means that Rust takes 143% the electricity or emissions over Rust. So at the lowest level and at the highest level that Node can perform at, it is at 181.58%. So it's 1.81 times the multiplier. Now, if we looked at how much kind of coal we would save if we burned coal at our location, this would mean that we would range somewhere between the coal saved using Rust instead of Node would be somewhere between 20 pounds of coal saved to 92 pounds of coal saved for switching to Rust, depending on our workload here. I've done some other things here. Looking at the maximums, the maximum that Rust was able to run this test at when I didn't rate limit, it was I was able to do 20 requests per second, and I was running at 67 watts of electricity used to hit those 20 requests per second. So that means that the bare minimum watts per request would be 3.35. While Node's maximum was 9.5 requests per second, and it used 67.5 watts for that, which means that the bare minimum watts per request was 8.05. So what does that mean in context? Because 1 request per second is pretty low. So imagine if I had a workload where I had to, my minimum specification for the workload was to meet 100 requests per second. So to meet 100 requests per second using these maximums, I would need 5 servers running at 20 requests per second to be able to meet that 100 requests per second minimum viable product workload. That the requirement to meet the requirement, I would need 5 servers running at 67 watts each. So that means to hit this requirement, I would need to use 335 watts of electricity to meet these requirements, which means that my kilowatt hours for the year would be 2,934, or my carbon emissions in CO2 would be 1,269 kilograms of CO2 emitted to meet these requirements, and that is with the Rust application running. For Node, I would need 10.5 servers. Now, there's no such thing as half a server, but the math got a little bit more complicated than the napkin math that I wanted to do. I would need 10 servers running at maximum, and then one more server running at a little bit lower wattage here. So bear in mind that these aren't exact values, because I am kind of pretending that half a server is a real thing, but half a server is not a real thing. The energy used in these calculations would mean that I would be using 805 watts of electricity in order to meet these requirements, which would mean my kilowatt hours yearly would be 7,054 kilowatt hours used, or my carbon emissions for that would be 3,051 kilograms of CO2 emitted to run this workload. That means that the node is at these levels. Node runs at 2.4 times less energy efficient than the Rust application to meet these requirements. So our carbon emissions are 2.4 times more if we switched from our Node.js server to the Rust server. So in this test scenario, which I admit is a very rare test, it's basically a very heavy workload to really grind the processor. In this case, Rust is a lot more than twice as carbon friendly as the Node application would be. Okay, so the next test was the very light load, and this is the file test. So in this test, I'm simply returning the HTML for a file, and the file is, in the Rust case, it is precompiled into the binary, and it is taking the a man page here, and this man page is it is just some HTML text, and I got it from man.7 looking up the man page for Open2. And if I ran that, if I run this in a browser, what I will see. All right, sorry about that. I had a little bit of problems with Firefox here, so I'm going to show you the file test. So it looks just like this. It's just returning an HTML version of the Open2 syscall website as seen on man.7.org. And if we looked up Open2 man 7, it is this web page, except it's run on either on the test. So yeah. So yeah, the code for this is as such. We are simply returning it out as, this is the entirety of the test. We're just returning it as HTML. And in the Node code, it's pretty much the same. It's just we're returning the HTML. So this is a very, very light test, just gathering information from memory and spitting it out via the various web frameworks, Express.js or Axiom. And the file tests are as such. Here is the information that I was able to gather. So for 100 requests, Rust used 15.5 watts of electricity. And I would like to remind you that the idle of the NUC being under test is 12.5, around 12.5 watts. So we're not running much heavier than idle for the 100 requests. Node used a little bit more at 18. For 200 requests, we're at 16 for Rust and 21 for Node. 400 requests were 17.5 versus 25. For 800 requests, we were at 19.5 versus 31.5. For 1200 requests, we were at 21.5 versus 35.5. And for the last test, which is 1500 tests, we were at 23.5 versus 38.5. So if we break it all down, this time I'm looking at milliwatts per request. We range from 155 for Rust at the lowest amount of requests per second to only 15 milliwatts per request for the maximum amount. Node had between 180 milliwatts of electricity used to 25.67 milliwatts of electricity used per request. The maximums for the requests per second for Rust and for Node were exactly the same. So we had the same speed performance characteristics in that both of these frameworks were able to run this test at 1580 requests per second at maximum. However, Rust used 23.5 watts again. There wasn't much difference between this 1580 and 1500 for Rust. And Node.js used just 1 watt more for the extra 80 requests per second. So running at maximum, we see that the milliwatts per requests for Rust was 14.87, where Node milliwatts per request is at 25. So given the, and here we can see the percentage difference between Rust and Node. So Node gets worse as the requests go on when compared to Rust. So at just 100 requests per second, we're only at 1.16 multiple for Node overhead over Rust, while at 1500, we are at 1.63 overhead, Node overhead over Rust. That means that the amount of coal saved is somewhere between 7.5 pounds to 44.5 pounds saved if we switch to Rust. And our carbon emissions for this would be between 58.75 for Rust at the minimum and 89.7 kilograms of CO2 emitted for the 1500 requests per second. And that's for the whole year. And over here we can see the amount of the kilowatts per hour used if I ran this for an entire year. So given the hypothetical scenario of we have a minimum requirement of serving 10,000 requests per second of this static web page. So just for context, 10,000 requests per second is about 1/5 Google search requests per second. Google is hitting somewhere between 50,000, 60,000 requests per second on their search box when you type something into Google. So we're at about 1/5 Google level here. So if we were at 1/5 Google level, what would we need to host this web page? For both Rust and Node.js, we would need 6.33 NUC servers to do this. You should be going like, oh my god, that's so little compared to like 10,000, like to 1/5 Google levels to host this web page, but this is an exceptionally light test. So we would need 6.33 servers. And again, I want to make it clear that, yes, I understand that 1/3 of a server is not a real thing. But for napkin math simplification, that's what we're going with. So over the year, what we would, the energy required to run at those minimum requirements for Rust would be 184 watts of electricity, while for Node, it would be 250 watts of electricity. If running this over the year, I would consume 1,303 kilowatt hours of electricity for Rust, which means that my carbon emissions would be 563 kilograms of carbon dioxide emitted. For Node, we would be using 2,190 kilowatt hours of electricity over the year, and we would emit around 950-ish kilograms of carbon dioxide to maintain our website. And this means that Rust at these minimum requirements, or the Node is a multiple 1.68 multiple of running the Rust. So we would save a lot of carbon dioxide. If this workload was running in Node and we switched to Rust, this is how much energy and carbon dioxide we would save. So I've been a little bit negligent. I haven't been showing you the graphs. Let's show the graphs. So for the file list electricity usage, here is kind of a graph of, here's the graph of the electricity usage for that first test. Here we can see the orange is Node, while Rust is the blue or the purple. I'm colorblind, so I can't really make it what that is. It's blue. It's blue to me. Here we can see the electricity use difference on a graph, so you can kind of visualize what's going on with it. And here is a carbon emission graph of the difference between running Node versus running Rust, where Rust is blue, Node is orange. This is for the first test, the file list heavy test. For the light test, the amount of electricity usage is visualized here. You can again see that Node is using quite a bit more than Rust. Not only that, but you see that Rust isn't kind of increasing as dramatically as the Node is. So Node seems to kind of, Node's in comparison to Rust, Node gets worse as the requests per second get higher in these two tests. And the amount of carbon dioxide emitted between these two tests for the light test, the file test, is visualized with this graph here, where you can see that at a low amount, the difference isn't all that much, but as we get up to the 1,500 requests per second, there's quite a bit of difference between Rust versus Node. So for the last test is the most real world of the tests here. And this is looking up from a Postgres database, getting data out of the Postgres database, and then turning it into JSON data that we then give to the client. So let me show you what happens when we open a website for this. So we get our nice JSON data here. And if we just look at the raw data, you can see it's, user identifier, first name, last name, user identifier, first name, last name, blah, 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 blah. Yeah, so there's 1,000 entries. We start at user identifier 1 and we go up to user identifier 1001. So the code for Rust, this is where the Rust code, you can see the complexity of Rust over JavaScript here. For Rust, we're running two functions here. We are running a first is like our first level of functions here, and this is our users. And in here we are calling a get user function. And this get user function is where the data is retrieved. After the data is retrieved, we turn it into JSON and return it to our user from this users function. In the get users, we are going to connect up to the SQL database. That is actually done in main here via the setting up the pool. So the pool is shared thread, and it's never mutated, so we can just we don't have to mutex that or anything of the sort. And it's passed in as the pool here to the get users function. So we're connected to the database and we start making our queries. So we're selecting star from users. We get the user identifier, first name and last name, and we get all of them. And then we transfer this into the file type that Rust knows in this user structure. And this user structure can be serialized. So after we gather all of this data, where we turn the user identifier into a U32 or into an I32, and then we turn the database's concept of a varchar 80 into the Rust concept of a string. After we do all that work, then because users is serializable, we can just get this JSON call to return JSON to our web page or to our user. You can see that the JavaScript code is quite a bit more simple. Here we are using the PG plugin as opposed to Rust uses the SQLX. So the PG is a pretty simple API where we just make the query, and we're actually using a pre-computed query on the database system for this. I tested both scenarios using what's it called? It's a procedure, an SQL procedure, pre-compilated procedure. I tested this versus just calling like select star from users, just like I did in Rust, and the performance was exactly the same. And this was just a little bit easier for me to read, which is why I used it. So in here, we just call the query. And if we do not get an error, then we stringify the data in each one of the items in the query, and we send it off to, we stringify all of the rows that come out of the database, and we send that off to the user. So the JavaScript code is quite a bit more simple than the Rust code. But yeah, what do we see in terms of the electricity used for this? Well, Rust fanatics, you are going to be a little bit sad here, because there's very, very little difference between these two tests. So in here, we have the 100, 200, 400, 800, 1300, and 1400 requests per second. For Rust, we used 22 watts of electricity for the 100 versus 22.5 for Node. For 200 requests per second, we used 28.8 watts of electricity in Rust versus 29 in Node. For 400 requests, we used 38 watts of electricity in Rust versus 39 in Node. So it's only when we get up to the really high amounts of requests per second that we start even seeing any real changes whatsoever here. So Node was not able to get up to 1400, which is important here. But at 1300 requests per second, Rust was at 71.5 watts of electricity used, while Node was at 75.5. So at that level, we're at about 6% more for Node. For milliwatts per request usage, We had between 220 in Rust and at the minimum 100 requests per second, and at 55 for the 1300. Compared to Node, which is at 225 milliwatts per request in Node versus at 1300 requests per second, we had 58.08. So there's not too much difference here. The important thing to notice is that Node could not run at 1400 requests per second, where Rust could. And that will mean something when we get into the hypothetical requests per second needed, the minimum viable product, the minimum amount of requests per second that we need to be able to kind of host our requirement analysis. Says it'll make it matters later on. I will discuss that in a second. So as you can see, our carbon emissions are basically the same between Rust and Node for these two, for this database test. Very little coal would be saved if we switched from JavaScript to Rust. However, if we had this 10,000 requests per second, if we are at the 1/5 of 1/5 Google level requirement, what this means is that Rust would only need 6.8 servers to handle this, while Node would need 7.35. That means that to meet this 10,000 requests per second requirement, Rust would need 520 watts of electricity, or it would use 4,558 kilowatt hours per year, meaning that Rust would cause 1,972 kilograms of CO2 emissions, while because we have to run more servers in Node to be able to meet these requirements, we would need to be using 577 watts at any one point in time to meet these requirements, meaning that we would need 5,056 kilowatt hours of electricity to meet these requirements, or we would be using 2,187, we would be causing 2,187 kilograms of CO2 emissions per year. So that means that the multiples, the multiple of CO2 emitted, because we would be using Node instead of Rust, would be 1.1, the factor that Rust would be using. So there's a couple hundred kilograms that could be saved if we were running at 1/5 Google level. If we want to check out these graphs, as you can see, the lines are very, very similar. But again, take notice that as the request per second grows, the difference between these two lines also grows. So the node is more steep than Rust. While the carbon emitted, as you can see, at 100 requests per second, it's virtually the same, and it's only minimally different at 1300 requests per second. But again, Node couldn't hit the levels of performance that Rust could hit, meaning that extra servers would need to be added for Node versus Rust. So what is the last thing that you should be asking? What you should be asking is, isn't bun.js supposed to be our savior for JavaScript? And the answer is maybe, but not quite yet. So I did run these tests under bun as well. So let me close these guys up, and I will open up my bun test. So my bun test is very, very similar to the Node.js test, with the exception that I couldn't figure out how to do routing with bun. So I kind of had to stop the test, run the file test, stop the test, rerun the file list test, stop the test. And then also Bun did not seem to have a plugin for Postgres database server, so I simply couldn't run the tests for Postgres for the user DB tests. I couldn't do it because I couldn't find a plugin for for Postgres SQL. So that test couldn't be run. Another warning that I want to give for Bun is that I was seeing seg faults in my applications when I was running this, and from other YouTubers that I've been watching who have given their opinion on Bun, they have stated that they have also seen seg faults when running their code on Bun. Um, and again, the seg faults I was seeing was on the file list test, and the file list test is basically copying and pasted from the Node.js test. So the Bun is not yet up to replacement for Node.js because there's bugs and because the plugin ecosystem isn't quite there yet. However, I do have some numbers for you. And for some reason, these are not captured in my graphs here, in my calculations here. Although I do know that I put them in, I guess I didn't hit save. So I've got them on my handy my handy pad of paper here. So let's look at the file list request. So sorry that I can't show you the numbers, but I have them right here in front of me, and I'll just list them off. So in the case of 1 request per second, Bun was at 20. So it was more than Rust, but less than Node.js. For 2, it was at 29. So again, more than Rust, less than Node.js. At 4, we were at 40.5. And at 8, we were at 60. And the maximums that I could get out of this were 11 requests per second. So it was a little bit better than Node.js, but it wasn't close to the amount of requests per second that Rust could do. For the file test, so I didn't bother to calculate to do the napkin math for the carbon emissions and stuff like that, because Bun is not yet a replacement that can be considered for running these things because it crashes. For file, I have the numbers here as well. For 100 requests per second, Bun was at 16 watts used. For 200 requests per second, we were at 18 watts used. For 400, we were at 20.5. 800 was at 23.5. 1200 was at 26. And 1500 was at 28. So quite a bit better than Node, but still not as good as Rust. So, Bun does seem to have promise within it. The promise is that it uses less electricity than Node. But of course, it is not up to snuff yet. There are seg faults that happen. And that means that the code to halt a seg fault is not yet in the Bun source code yet. So there is more code that will be put into Bun, meaning that Bun will run slower and less efficiently in the future, because at minimum they have to go, if about to seg fault, don't seg fault. That sort of code segment. If value returned equals null, don't dereference null pointer. That sort of thing. There is more code that Bun needs to put into its source code before it's even really testable. And that's why I don't want to go too in depth about it, but it shows promise at being better than Node, but not quite there yet with Rust. And of course, because there is no Postgres SQL plugin, I really have no idea about how it's going to perform there. My theory is that it will be very, very close to Rust levels of performance. because I think a lot of the electricity used in both Rust and Node upon the UserDB test is actually electricity used by the Postgres database rather than the transfer of the data rows from the database into JSON. Yeah. So I hope that you have at least been entertained, learned a little bit something about Rust versus Node and how their efficiencies matter, especially in terms of the carbon footprint that these languages place upon the world. I hope that if you are a scientist with grant money and you have an interest in how the field of computer programming can lower its carbon footprint, I hope you can do a much more in-depth test than I could do. I hope this inspires you to go, yeah, that's a good idea. Too bad that guy can't do all the real hardcore sciencing things. I can do that. I've got the money to do it. I've got the budget to do it. Let's do it and let's really answer this question. So yeah, thank you very much for watching. Again, please, I put a lot of work into this, so if you did find this, if you found this message important, please share it and like the video, because I do want this message to be spread that yes, Rust can help us with our carbon footprint as computer programmers, although it might not be the panacea that we all pretend it to be, or that internet bloggers pretend it to be. Thank you very much for watching and have a nice day.